Greetings, the Astro 30 here yet again, and welcome back to AEL. And firstly, Happy New Year to you, and also welcome to the first video of the new year, 2026. Now today I want to go through and I want to make a series of videos out of this, of designing a power amplifier to power a speaker. Not particularly this one, because, well, this is an old Magnavox. And I'm not sure what that thing is, but it looks quite interesting. I think that's part of a tree. Part of a tree. Anyway, this speaker is just here as a reference on the desk for something to be in the frame of the video rather than having nothing. So let's go through the basic building blocks of a power amplifier to power a speaker like this that we need in order to make the thing work. Well, before we can build anything and create an amplifier from scratch, which is the whole entire premise of this video series, we need to know the basic building blocks of the amplifier so we can implement them correctly. Now, here's a basic block diagram of how an amplifier, standard amplifier, works. We've got our input stage here, or long tail pair, LTP in this case. There are various different types of input stages, but I'm going to keep it as simple as possible, just a standard LTP with a constant current source, which in the preliminary design can just be a fixed resistor, but can be upgraded to a proper current source later. We've also got a current mirror. In this case, this is not going to be implemented in this video, but will be implemented in a later video. We've got a constant current source for the bias network and voltage amplifier, which comes up with the input stage. The biasing circuitry here drives the P driver, which is the positive going cycle side, and the N driver, which is the negative going side of the cycle. So this would be an MPN up here and a PNP down here, and it's operating in class A. And then we finally have our output stage, the P side and the negative side. And in my case, I'm going to implement it as a Darlington or emitter follower style output with negative feedback going back to the input stage. We'll also notice these two boxes here saying decoupling. That's DC decoupling, so that's just a simple series resistor and a capacitor to ground on both sides. It just separates the input side and voltage amplifier side from the high current output side, just to help with stability of the amplifier. In practice, this is generally not needed, but it wouldn't hurt to include it. Now I'm going to be using a simulation program called Texas Instruments Tina, and we can actually draw the entire amplifier schematic out in Tina and run a simulation on it of DC tests and AC tests to see if our concept is going to work before breadboarding it out, which I'll go through shortly. But first, what I want to do is I want to test input stage here. So this is our basic input stage. Now it's not connected to a voltage amplifier, it's just the two input transistors. This is our fixed current source, which is a 47k fixed resistor. That's the decoupling, 100 ohm and, well, I'd say a 47 microfarad, both here and here. We've got two collector resistors of 4k7 each, and we're going to be probing or scoping the output of each collector. So what we should see on our oscilloscope is a signal off of this transistor going in the normal 0 degree phase, and on this collector we should see a 180 degree signal out of phase with this one, and they should be roughly about the same voltage amplitude, and that gives us an idea of, well, how this actual circuit works. So let's go to the breadboard and have a look at that particular circuit here. This obviously is not going to be the final design because, well, we wouldn't have this base 22k resistor going to ground, which is earth lifted by this 10 ohm resistor here. But it gives us a proof of concept of how this stage actually is supposed to work. Okay, so I got the input stage that I want to test built up here on the breadboard. There's my input capacitor, and I'm probing each of the 4k7 resistors that go to the negative rail at the collectors of each transistor. Circuit is powered up and we've got a signal going into the input, and there's our output there. Now the top trace is measuring the first transistor, and the blue trace is measuring the second transistor, which is normally the one that does the error correction in the amplifier or the feedback side. And as we can clearly see, both signals are 180 degrees out of phase with each other, which is what we expect, because that's exactly what the long tail pair circuit does. And we can also see they're producing roughly the same output voltage of 777 millivolts, epic, RMS. Well, that's great and all, but it's not very useful. Okay, so as we saw, this input stage did actually produce two outputs out of phase with each other at roughly the same amplitude of 777 millivolts. It would have been funnier if it was 666 or even 69. Anyhow, this is not very useful as an amplifier. It proves, yeah, what these two transistors are doing, because it's the same as op amps really, that each transistor tries to make its input the same as the other, and that's exactly what this circuit is doing. So before we move over to the Tina, I want to go through the prerequisites of the final design of this amplifier. So we have a basic building foundation to go on. Okay, so here's my list of prerequisites for this particular amplifier design. It has to be simple, so no overly complex circuitry, including in the input stage and voltage amplification stage. It has to be able to push at least close to 50 watts into 8 ohms at a voltage supply rail of plus minus 35 volts. Relatively low DC offset without having to add a offset servo, which may have to be implemented in the end or not, I don't know. Relatively low distortion. Now, Tina can measure the distortion or total harmonic distortion of the design. That's using ideal transistor models. In the real world, the results are going to differ, but if we can get a distortion under 0.02%, that's doing pretty good. Good stability as in thermal and sonic, so it can't go into spurious oscillations by itself, and it can't go into thermal runaway. A good frequency response without adding any extra colour to the sound. Made from common parts, so no obscure transistors. Preferably an adjustable bias, and audiophile friendly, that is, you don't add any extra stuff in the output such as fuses, PTCs, or even a VI limiter. So that would also negate short circuit protection as well, but you can't have everything. So let's flip over to Tina and we'll have a look at the first schematic that I've come up with. Okay, so here's a look at the first version of my power amplifier schematic that I've came up with in Tina. And using Tina's simulation software makes it a lot easier for sorting out problems with like inadequate current in the output stage, too much current in the output stage, etc., and working out all the resistor values so you don't actually start blowing up transistors and smoking resistors. So currently we've got just a simple long tail pair with a fixed resistor as a constant current source, 4K7 down here in the collector, which goes off to a single transistor for the VAS, which has an emitter generation resistor here of 68 ohm. Technically this resistor isn't needed, but it does help control the current flow through the VAS, plus does affect a DC offset on the output. Biasing arrangement is simple. We've just got a 1.2K resistor and a string of 3 1N4148 diodes. Now I tried 2, but the current in the output stage was in the microamps way too low. So that's the reason why there's 3. If I messed with the values up here properly and more in depth, maybe we could have got away with 2 diodes, but it's really neither here nor there. Got the DC decoupling here with these 2 resistors R11, R12, and these 2 47 microfarad capacitors to ground. The gain of the amplifier is set to 23, and that's something I forgot to mention in the prerequisites. We don't want lots of gain, we just want a standard gain of 23. Over here I've got my power supplies, which is plus 31 and minus 31 respectively, which is linked to these 2 points here. So I've got a function generator roughly putting out 1 volt amplitude and 1 kilohertz at the input here, And I'm just going to run the analysis of the DC side so we can see what we get for current draws and voltages, etc. So I've got an amp meter in series with a positive voltage rail, and as we can see, we should see around 50 odd milliamps here. But the problem with that is, if I click on that and then bring this into view, voltage of R8 has a drop of 27.47 volts with a current of 22.89 milliamps going through it. That equates to around 725 milliwatts of dissipation, which is going to be totally over the current handling of the half watt resistor that's going to be there. So that's going to be a problem, and even a 1 watt here would be slightly warm. So in the end you'd have to use like a 2 watt resistor. So immediately this circuit is out mainly because of that. I mean, that could be corrected by adding a VBE multiplier here instead, but that's to be explored later. But what I was trying to achieve was roughly 20 milliamps of current going through the output stage here, which is what we've got. And if we take a look at our output voltage, we can see we've got 404 microvolts or so. Now, that's going to be, in the real world, probably higher or lower depending. But for now, it looks like the DC offset's pretty good. And we've got roughly 22 milliamps going through our VAS here. As to what its total harmonic distortion is, I've just run the Fourier series test. We get 0.26141%, and that's at a frequency of 1 kilohertz. Yeah, it's not great, but for a first design, it's not bad. So, as I say, because of this resistor value here and its wattage handling capability, this idea is out. So I've come up with a version B to this. And this is version B. Now, it's basically the same, except now we've got two 680 ohm resistors in series with each other. And if I run the DC analysis on this, well, we've got 17 milliamps or so running through the output stage, which is fine, and about 43 milliamps being drawn from the power supply. If I click on this 680 ohm resistor, well, we've got 13.86 voltage drop across the resistor and 20 mA going through it. So we're going to be around about 300 milliwatts of dissipation, which is within the half watt of the resistor, but it's still going to get quite toasty warm. So we'd be better off using a 1 watt device here if this was going to be a final design, or 2. But doing this leads us to be able to bootstrap between this point and the output to improve the gain of the output stage, which is something I'm going to try in this video. Other than that, apart from the DC offset being slightly higher at 1.14 millivolts, it's pretty much the same as the first schematic. So if I now do a total harmonic distortion test on it, it's actually worse. It's 0.57209% at 1 kilohertz. Yeah, okay. Again, for a first design, that's fine. We can always modify the circuitry around, including the values of the constant current sources, etc., to get the distortion to come way down, which will be explored throughout this video series. But for now, I'm going to build up this particular circuit and see if it actually works. Tina says it works, so I expect it to work. However, before I do that, it might have been a good idea to run the frequency response test in the simulation, which I have done so now, and as you can see, between 10 Hz and 1 megahertz, the signal is relatively flat all the way up to at least 30k. So that's a good starting point. Of course, this doesn't beat real-world measurements either, but it's just a good starting point. So here's my working prototype. It works very well, produces 100 watts into 4 ohms and picks up background microwave radiation from the universe. That's so fucking stupid. Alright, I'm going to stop being a bellend now. Alright, all jokes aside, here's the actual circuit implemented up on the breadboard. That's just a piece of anti-static foam. That's not going to do anything. So currently I've got the power supply set at plus minus 31 volts, and all the tests on this amplifier will be done at that voltage. And I currently don't have an input signal going, but I'm measuring the output points here between here and ground on a multimeter to see what our DC offset is. Our power supplies are currently off. I've got them set to roughly 200 mA current limiting. So if I turn the supply on, well, right away we've got a reasonably good low current draw, but it's a lot less than what Tina predicted. But again, that's because of ideal transistor models. Now, as we can see for DC offset, we've only got around -3 millivolt, which is pretty close to what Tina predicted. So I'm happy with that. And if I touch the input with my finger, a wet finger, we can see it's jumping around. So I can already see that this thing is working as an amplifier. So with the output connected to the oscilloscope on the lowest possible voltages per division, with the oscillator disconnected from the input, if I touch the input, we can see that we're getting the blurt test. So that's already proven to me that it's working as an amplifier, which is great. However, these 680 ohm resistors are getting quite warm, as I said they would do, and so is the bass, but there's like 20 mA going through that, or close to it. So that's about a watt of dissipation. So it would need a heatsink on the VAS and most likely 1 watt resistors here for the 680s, if this was to be the final design, which it is not. So I'll connect the oscillator to the input, and as we can see, we're getting a nice output signal. However, it is asymmetrically clipping, so we can see the bottom is clipping earlier than the top. And it's not loaded, it's only just measuring the output directly. I will load it in just a second. I just want to show what I meant about bootstrapping between these two resistors and the output bus. So what I'm going to do is I'm going to gently touch the negative of this capacitor to the output, and we'll watch what happens on the scope. That's without the capacitor connected, that's with it connected. As we can see, disconnected, that the amplitude of the signal increased a little. However, I don't know if that's going to really help us with asymmetrical clipping. No, it's not, because we can see it's still starting to asymmetrically clip here at the bottom, which, well, that could be the biasing arrangement that I've got so far. But all in all, it is producing a signal. So what I'll do is I'll load the thing into an 8 ohm dummy load, and we'll just see, well, how much power it can produce out. I'm going to predict around 35 watts at this power supply rail, which is perfectly fine. And I'll just disconnect the bootstrapping. Okay, we are loaded. Actually, I wish I was loaded in more ways than one. Okay, so I'll turn the supply on. Still reasonably good current draw. Nothing should blow up at this point, so I'll increase the oscillator. There's our signal. And there's asymmetrical clipping. Back it off. 15.2 volt roughly. So let me calculate what that is. 28 watts, not bad. So let's try it with the output bootstrapped. That was a 47 microfarad capacitor, by the way. So there's our signal. There's asymmetrical clipping, so it's not really helping asymmetrical. Back it out. Well, now the signal's more like 16.2 volt with bootstrapping. If I just remove the capacitor out of circuit, well, it's not clipping, but the voltage drops off. So this demonstrates why a lot of power amplifiers are bootstrapped, because it improves the gain of the output stage. Nothing's smoking. Those are getting quite hot though, so that is a concern. So at 16.2 volt RMS, we're closer to 32 watts. So that was to be expected. So what should we do now? Well, we really should do a frequency response test on it. But I'm pretty sure, according to what Tina was saying, the frequency response should be flat between 10 and at least 30k. So I don't really need to do a physical frequency response measurement. I will do on the final design, but for this design it's going to be changed anyway, so there's no real point. What I will do is I'll hook it up to a speaker and a sound source, and we'll give it a listen to what it sounds like, and then we'll close this one out, because I've already gone through the basic design, and in the next video in this series we'll be exploring constant current sources, maybe a current mirror, see what differences it makes to our circuit, plus VBE multiplication instead of these 3 diodes, and that'll be something rather exciting. Okay, the amplifier's hooked up to the computer and a speaker. There's hardly any noise coming out of the speaker apart from a slight buzz from the input connections down here that you can't see. But that's perfectly fine. That's probably not a good test speaker because of the size of the driver, so there's not going to be that much bass response, but I'll certainly hear if all the frequencies are there. It sounds alright. That's probably not the best track to test it with. That'll do for that. That's actually not a bad sounding track, I must admit. As I said, the size of the driver in that's only like 110, 120 mil, something like that. Is not going to give a very deep bass response. I mean, it says on the back of this speaker that its frequency response is from 150 Hertz to, I think it's like 16 kilohertz or something. We heard we got good sound out of this amplifier, and obviously not that one. We know the concept works and that it's a good starting point. By the way, the output devices I'm using are 2SC 1500 and 2SA 1943. So different output stage transistors compared to what's in Tina is going to reflect A, on what the current draw of the circuit is doing, which is why we've got a discrepancy. Tina says 43 mA quiescent current. My power supply, albeit it's probably about 2 milliamps out, says 35, but different output transistors as to what is simulated, and Tina doesn't actually have them by default. You'd have to download third-party models and stuff. I can't bother messing around with that stuff. But overall, we've proved that the simulated design actually works in the real world. So in the next video, as I said before, I'm going to expand on this, modify it, adding a constant current source, maybe a current mirror, as well as a VBE multiplier to overcome this problem with the two 680 ohm resistors here getting quite hot. And yeah, we'll go from there. So look out for that. So I hope everyone had a happy new year. I know mine started off with a bang, not literally though. And yeah, I'll see you in the next video. I'm the Astro 30, and if you enjoyed this video, please remember to go down below, like, comment and subscribe if you haven't done so already. And as always, this is the Astro 30 saying see ya, thanks for watching, have a great day.